right, guys, let's talk about 3.1. It's about predicates and quantified statements. So the main part of this section is going to be dealing with predicates. It's basically a statement, similar to a statement, but a little bit different. We'll talk about the definition in a second, and then we'll also have quantifiers. So we're going to learn about all the different symbols that we use for quantifiers. Okay. But anyway, here's a definition, which I'll send in a second. Post this in a second after today. A predicate is a sentence that contains a finite number of variables and becomes a statement when specific variables or values are substituted for the variables. The domain of a predicate variable is the set of all values that may be substituted in place of the variable. Okay. All right. So let's do an example, 3.11 in the book. So let P of X be the predicate that is X squared is greater than X, with domain of the set of all real numbers. Okay. So part A, find P of 2. B, find P of 1/2. C, find P of -1/2. All right, so P basically is this predicate here, okay? Put in quotes. So if we plug this in, let's see if this is true. So all they want us to do is plug it in, really. Is 2 squared indeed greater than 2? Is 4 greater than 2? And then, of course, the answer is true, right? So this is the actual statement, which then has a true or false, right? Before you input values, it's just a predicate. That's what the definition is saying, right? It's a sentence that contains a finite number of variables and becomes a statement when you substitute specific values. Okay, so it becomes a statement when I do this, right? That gives me 1/4. Is 1/4 greater than half? False, right? Now, is -1/2 squared greater than -1/2? Well, that would be 1/4. Is that greater than -1/2? And the answer is true. Let me separate this. Got a little too close there. So that's what a predicate is. It's something that can become a statement once you plug in values. So this P of X is a predicate that is representing this. Okay. All right. Let's try another definition here. Okay, so this next definition is a little bit more important because, as you saw with the predicate, it seemed kind of almost meaningless, right? Like, well, why do I care about P of 2 or P of half, P of -1/2? Well, eventually the ones we will care about are the sets of values that makes it always true, that makes a predicate. Well, basically, you can find a collection of values that makes your predicate into a true statement. Like, where is this truth set located, right? So if P of X is a predicate and X has a domain of D, the true set of P of X is the set of all elements of D that make P of X true when they are substituted for X. So then the truth set of P of X is denoted as this. So all the X's in the domain such that P of X, just that they're in P of X. So just do an example so you can see what I'm talking about. Okay, excuse me. Okay. So finding the truth set of a predicate. So let's let the predicate be denoted as Q of n. Let Q of n be the predicate. Which is representing n is a factor. Let this one fit there. Let's do it over here. N is a factor of 8. Okay. Find the truth set of Q find the truth set of Q of n if, okay, here's part A and part B. 1 second. Okay, so Q of n, so we'll pick 2 different domains for part A and part B, and we got to locate what the truth set is, right? So the domain of n, they're basically defining that n is in Z positive, Z standing for the set of integers, but only the positive integers, set of all positive integers. The domain of n is in Z, capital Z, the set of all integers. So the answer for A, right? What are the factors of 8, right? That's a predicate, that live in the positive integers, right? So the set would be, factors of A would be 1, 2, 4, and 8. These are all factors of 8 that are in the positive integers. Now part B, the domain of n is capital Z, the set of all integers. So it's going to contain these, but also the negatives. So we'd have to write down the negatives. So I'm going to go ahead and write the same ones because those are there, right? Who cares? That'd be -1, -2, -4, -8. That makes sense. So basically, there are 2 different truth sets depending on the domain that is chosen. And that's what we're going to be doing in the homework as well. All right, let's talk about the quantifiers. So the universal statement, or the universal quantifier, is of the form, this is little upside down A, for all x in D, Q of x. So basically it is defined to be false if and only if I'm sorry, let me double check that. Defined to be true. I don't know why I wrote that. Weird. It's only true if all x satisfy the statement. So it needs to be true for all x in the domain. It is true if and only if q of x is true for all x. Okay, so if there's one x that makes this statement, this predicate or statement false, there's one x that goes against this some statement, right? For universal, then that means the entire thing is false. This entire statement is false. Now for existential statements, so it is a statement of the form to the backwards e. This means exists an x in D such that q of x. So there's some random statement that says there exists an x in this domain of q. So this will be true if at least one x in the domain satisfies this statement. So qx is true for at least one x in D. So the only way this would be false would be if all of the x's are false, are not fitting the statement. Okay. So the definition in the book are a little longer, but I think I shortened them up just save some time. Please look them over when you get a chance on page 110 and 111. But let's get to the examples. It's example 3.1.3, truth and falsity. Of universal statements. Okay, so part A. So let the domain D equal the set 1 through 5. 1, 2, 3, 4, 5. And consider the statement. For all x in the domain D, so remember that is epsilon, right? For all x epsilon D means for all the x's in the domain D, this statement is true. Okay. So the question is going to be right one way to read this statement. Out loud. Okay, so I just said it right now, but let's go ahead and write it. So in English, right, for all x in D, this is true. So you could say for all x or for every x in the set D, x squared is greater than oops, or equal to x. And we can show that simply by plugging them in, right? we plug in 1, 2, 3. It's going to keep on being true, right? So yeah, 1 is indeed greater than or equal to 1. 4 is indeed greater than or equal to 2. 9 is indeed greater than or equal to 3. 16 is greater than or equal to 4. 25 is greater than or equal to 5. Right, so this is true for all x in this domain. So this shows us that it's true. Okay, so the question would probably ask you to show that it is. So hence, for all x in D, x squared is greater than or equal to x is true. Okay. Okay. Part B. Consider the statement, so part B here. For all x in R this time, x squared is greater than x. So the instructions are find a counterexample, because one example will show one example that violates this, x squared greater than or equal to x, will disprove it, basically show you that it is not true. And since they said that domain now is R, meaning you can choose any number that is part of the real numbers, which is all the numbers, right? And as we saw in the last example, if we let x equal to 1/2, right? 1/2 squared is not greater than or equal to 1/2, right? Because you get the fourth. So this is a counterexample. So this statement is false. Right here. For all x in R, this is true. It is not true. Okay. Let's go on to the existential quantifier. Okay, so here's first part, part A here. Truth and falsity of existential statements. So translate the statements to English. This will be the first part. That will be the first part, and then we will show if they're true or false. Okay, so there exists an M, epsilon z plus, meaning there exists an M in the positive integers, right? That's what that means. Such that M squared equals M. Okay, so let's put it in English, right? Quick translation. So they'll have you do that in the homework as well. So there exists an M such that M squared equals M. Is that true? Well, remember we said for existential quantities, right? All we need is for one M to be true. We just need one of them. So an easy one that's positive integers would be 1, right? The number 1. 1 squared equals 1. Therefore, this statement is true, as long as I have 1. Okay, part B. Let E, capital E, equal 5, 6, 7, 8. Okay, sorry. So for B, we got that guy there. So the statement would be there. Oh, let's just go ahead and write it in symbolic form first. Okay. There exists an M in capital E, right? It's the set that we're dealing with. Such that, right? So this is a straight line. M squared equals M. So is that true? No, all we need is 1 for it to be true. If I square this guy, I get 25, 36, 49. So no, it looks like none of them will be true, right? 5 squared does not equal 5. 6 squared does not equal 6. 7 squared does not equal 7. 8 squared does not equal 8. So all the elements in E are not satisfying the statement. Therefore, this statement is false. There does not exist an M in E such that M squared equals M. All right, and the translation, of course, I just said it, right? The translation would be that there, forgot to write it, there exists an M in E such that M squared equals M. So this is the translation. And this is my answer here, my 2 answers. Okay, for part B. So the next few questions will be just translating a statement that's already in just symbols and change it into it's an English statement. Okay. So I don't think that's really worth doing. We just did it here. Let's go ahead and do just one, I guess. Example 3.1.5. translate the following. I'll just do part A. For all x in R, x squared is greater than or equal to 0, right? So in English, that means for all x in the real numbers R, x squared is greater than or equal to 0. So that's pretty much it. You'll have a couple of homework problems like that. The next one will be translating to formal language. So you will see that some things are informal. For example, so translate the following to formal from informal, right? Obviously. All triangles have 3 sides. So that's the same thing as saying, right, if we change it to symbolic, right? For all triangles T has 3 sides. So we basically create a variable for all triangles, right, or for a random triangle. So all the triangles T, comma, T has 3 sides. So it'll be pretty much something like that. For example, part B, no dogs have wings, right? So you would say for all dogs D, for all dogs D does not have wings. That's pretty much it for those examples. So let's move on. Okay, something else here. Okay. One moment.